Hey everybody, my name is Eric. I'm a tutor for this class, and welcome to the walkthrough for one of the practice midterms that we've released for this semester of Data 8. This midterm is pretty much the one that was given in spring of 2016, except we've taken the last question and changed it to fit the content that you guys have covered up to this point a little bit more accurately. Before we get started, I would suggest that you take the time to walk through this yourself, try the questions. It'd be super useful to do it under a time situation, but what's most important is just that you've taken the time to think through these problems before seeing the solutions and walk through. Now, with all that being said, we can go ahead and get started. All right, so this first question is on Python expressions, and what it wants you to do is it wants you to write a Python expression below each of the following descriptions that computes its value. We have this array of integers called CA. It has the population of California every 10 years, which means that the first item, index 0, has the population of 1900. The second item, which is index 1, has the population of 1910, and so on and so forth until we get to the very last item. Do notice that the indices line up with the decades that they represent. So this is index 0, which means it's 1900. Index 1 is 1910, index 2 is 1920, etc. Keep that in mind when you're answering these questions because you'll want to know that you're grabbing the right year. So the first question is the population change from 1940 to 1960 as a number of people. And in order to do that, I should find out what the population is in 1960, find out what the population is in 1940, and I'll take the difference of the two. So the population in 1960 is item 6, and the population in 1940 is at index 4, right? So this is the population in 1960, subtract the population in 1940, and it gives me the population change between 1940 to 1960. And it is a number of people, because if you subtract the number of people from the number of people, then you get back a number of people. Whether the population ever grew by less than 500,000 in a decade represented by CA. So first of all, I need to calculate each of the decade by decade growths, basically, right? So for example, if I want the population growth in the decade 1940 to 1950, I say CA.item of 5 minus CA.item of 4, right? This gives me the population growth in the decade from 1940 to 1950. And I want to do this for every pair of elements that are in my initial array, every pair of items that are next to each other, that is. And in order to do that, I don't want to have to write out this expression over and over again. So I have a function that'll do that for me. And it looks like mp.diff of CA. Hopefully you've used this before, and hopefully it's on your cheat sheet as well. But yeah, what this does is it takes every pair of elements that are next to each other in my array, and it gives me the difference between those numbers. So if I were to just write this out explicitly, it would look something like CA.item of 1 minus CA.item of 0, CA.item of 2 minus CA.item of 1, so on and so forth until we run out of elements, right? So this expression right here is equal to this array that I've drawn over here. The next thing I want to do is I want to compare everything in this new array to the number 500,000 and see if it's less than 500,000. In order to compare everything in an array, we can just compare the entire array to that number, right? So I say less than 500,000, right? So now what this whole expression evaluates to is if my first item was less than 500,000, then I'll get true. And if it wasn't, then I'll get false. If the second item was less than 500,000, then I'll get true. If it wasn't, I'll get false, but I'll just leave it as true for now, so on and so forth. So yeah, you just get a whole bunch of falses and true. It'll be true in places where this was less than 500,000 and false in places where it wasn't. And so that's what this whole expression evaluates to. And now I want to see if any of these are less than 500,000. So in order to see if any of them are less than 500,000, I have a NumPy function called mp.any. And what mp.any is it just takes an array and it tells you if any of them are trues, right? If any of them are trues, then this function call gives you true. Otherwise, it'll give you false. And that's what we want, right? The question asks for whether the population ever grew by less than 500,000 in a decade represented by CA, and it wants it as a true or false, and that's exactly what this expression does. The next thing we want is the annual yearly growth rate from 1920 to 1930. So recall our growth rate equation looks like this. So final population, which I'm calling P prime here, is equal to initial population times 1 plus the growth rate, K, and we want to raise it to the T, where T is the time that's elapsed. And make sure that T is in the right units, right? Because we want the annual yearly growth rate, then T must be in years. If we wanted the monthly growth rate of something, then T would be in months. So just be careful of that when you're answering questions like this, right? So in this case, we want the annual yearly growth rate from 1920 to 1930. And we know that in a decade, there's going to be 10 years. So there's going to be 10, T is 10 in this case. And what's the growth rate? Well, that's what we're trying to calculate. So we'll leave that as our variable for now. Okay, what's our start population? Well, our start population is just CA of item 2, the population in 1920. And our final population is CA dot item of 3, the population in 1930. Now that we have this algebraic expression, we can just rearrange it. So we have divide CA dot item of 2 from both sides to get rid of this. Then we raise both sides to the 1/10th power in order to get rid of the exponent. So I raise this to 1/10. And then all I have left on the right-hand side is 1 plus k, which means that I just subtract 1 from both sides. And that gives me k, my growth rate. So if I just delete this, then this is the expression that gives me k in Python, right? Yeah, and so that's the answer to that particular question. Now what I want is the population in 1924, and I assume a fixed exponential annual growth rate from 1920 to 1960. So that means, again, we can use our growth rate equation, or our growth equation. And this is what that looks like, right? And so now it says you can use the name G for the annual growth rate from 1920 to 1930. So I replace K with G. So that's given to us, and we just leave it like that. What's T in this case? Well, once again, we're working with years. But in this case, we're interested in the time period from 1920 to 1924, right? So that's only 4 years as opposed to the 10 that we had up here. Now we know that the initial population that we start with is the population in 1920, which we can pull from CA. So CA dot item of 2. And so what we're trying to calculate is the final population, right? The final population in 1924 is our unknown. And so if we get rid of that now, this is the Python expression that calculates our unknown. Okay? And so that's our answer to this question. The very last one asks us for the number of items in CA that are at least twice as large as the population in 1960. So once again, we're going to be comparing the whole array to some single fixed number. Okay? So CA, all right, the number of items in CA that are at least twice as large. Okay, so we want the item in CA to be larger. Okay, and it needs to be twice as large as the population in 1960, which is CA dot item of 6. So this expression gives us a new array, right? A new array of whether the item in CA is greater than this number of 2 times the population in 1960. So again, this is just like what we had up here, an array of trues and falses. And now, instead of whether any of them are true, we want the number that are true, right? And so the way we can do that is we can say mp.count non-zero, right? Because we know that in Python, we can consider trues as 1s and falses as 0s. And so mp.count non-zero just counts the number of 1s that we have in our array, which gives us the number of trues. The number of trues will be the number of items in CA that are at least twice as large as the population in 1960. Okay, so the second question is also asking for a Python expression, but it relies more heavily on your knowledge of stats. So here's your question. You got 1,000 different shirts, 2 of them are red, and you want the chance that during a 30-day month you never wear a red shirt, given that you put it back at night every night. So we can recognize this immediately as a sampling with replacement problem because you put back the shirts at night. So over this 30-day month, you're always going to be picking a random shirt from 1,000 different shirts. Okay? So this is sampling with replacement, right? Which means that the probability on any given day of not wearing a red shirt is going to be exactly the same. And the probability of not wearing a red shirt on any given day is 998 over 1,000. We know this because we have only 2 red shirts, so there's 998 shirts that aren't red. So the chance of drawing a shirt that isn't red is 998 over 1,000, right? 998 ways to draw something that isn't red over 1,000 ways of drawing any shirt at all. So this is the chance of not wearing a red shirt on any given day, and we want to figure out what the chance is that I never wear a red shirt. So the chance that I never wear a red shirt is the chance that I don't wear a red shirt on the first day, times the chance that I don't wear a red shirt on the second day, times the chance that I don't wear a red shirt on the third day, so on and so forth until I get 30 of these, right? And so pretty quickly, I think you can see that this is just 998 over 1,000 raised to some power, and the power that we raise it to is, of course, 30, right? So 30 days, for all of those 30 days, we want to not wear a red shirt. So we take the probability of not wearing a red shirt on any given day and we raise it to the 30. So question 2 is all about tables. 2a says the table named twins has a row for each pair of twins that contains the height of each twin in inches. So I've drawn that up already right here. Basically, we can imagine we have a 2-column table with the twin 1 and twin 2. Each row corresponds to a pair of twins. So each row corresponds to a pair of twins, and each column is like, with one twin out of the pair, right? And so we've defined this function diff height 1, height 2 that takes in a height and a second height, and it returns the absolute difference of those two heights. Okay, the second line is diffs is some table with one column called absolute differences, which is what I've drawn right here. And then it says for I in np.arange twins.num rows, which means for this loop is going to run for the number of rows that I have in this twins table. And for each loop, I want to append to this table the result of the function diff applied to each entry in a row. So you can see twins.column of 0 item I, twins.column 1 item I, right? So it's the same item from each 2 columns, which means that we're just taking, both entries out of a single row, and we apply the diff function to it, which remember returns the absolute differences of the heights. And so you can imagine this whole loop just creates a new table with the same number of rows as twins, except each of the entries in this single column is the absolute value of the difference between the twin heights. And then this last line takes the average of everything in this single column that we have in this new table. So it's a really long and complicated way of just calculating. What we actually want is the average absolute difference in heights, right? So how can we do that in a more simple way? Well, we can use array arithmetic, right? So let's see. What I want is the average absolute difference in heights among the twins, okay? So a good way to sort of do something that has a whole bunch of different words like this is sort of just work back to front, right? So first of all, we want difference in heights among the twins, okay? All we have to do for that is we have to say, okay, let's say twin 2. So twins dot column of first column, or column 1, so that's this column right here, minus twins dot column 0. Okay, I'll increase the font on this. So twins dot column 1 minus twins dot column 0 gives us a new array of the differences of every single pair of twins in this twins table, right? Now I want to take the absolute value of every single one of those entries, and in order to do that, all I have to do is just call absolute abs, or np.abs also works, on this whole expression here, and now I have the absolute differences in heights among the twins, And then what's the average? Well, I already have this right here, right? np.mean of this whole expression will do exactly the same as this whole code chunk, and I've done it without calling diff and without using a for statement. So the second part of question 2 is we have this trip table from lecture. Each row describes a single bike rental in the SF area. Durations are integers representing times in seconds, and we want to note that even though we only see 3 tables, there's quite a few more in the actual full trip table. Once again, we're writing Python expressions below each of the following descriptions that computes its value, but this time we can use up to 2 lines and also introduce variables. So the first bullet is asking what's the average duration of a rental that lasted more than 2 minutes. Again, I kind of want to work back to front in this case. I want to find all of the rentals that lasted more than 2 minutes, and I just take the average duration of all those. So how do I find all the rentals that lasted more than 2 minutes? Well, I'm finding a subset of my table that fulfills some condition. So that tells me I probably want to use the where method. So I go trip.where. And what do I care about? I care about the duration column. And what I want the elements in my duration column to be, I want them to be bigger than 2 minutes, which means bigger than 120 since it's given to us in seconds. So r.above 120. And so this gives me a new table of every single rental that lasted more than 2 minutes. And I'll call this table 2mins. Next thing I want is I want the average duration of all these rentals. And so once again, I'm just caring about this duration column. So I also have I have this duration column in my new table of 2mins. And so we know to calculate an average of some numbers, we add up all the numbers and we divide by the number of numbers, right? So first of all, let's add up all the numbers. All the numbers is the numbers in the duration column. So 2mins.column duration. Okay. Now I have this array of every single duration in 2mins, and I want to add all of them up. So I use np.sum, and np.sum takes in an array, and it spits out the sum of everything in my array, right? And then, so now I have the sum of all of the numbers, and now what I want? Well, now I want the number of numbers that I had. So the number of entries in the column duration. Well, I know that the number of entries in my column is exactly the same as the number of rows that I had because it's in a table. And so I just say divide all of this by the number of rows in 2mins, which I can get by 2mins.num rows. And so this whole thing, this second line right here, evaluates to the number that I want, which is the average duration of a rental that lasted more than 2 minutes. Okay. The second question, the number of rentals that started at the SF Caltrain station. Once again, I want to sort of work back to front. So all of the rentals that started at the SF Caltrain, and then how many are there, right? So once again, I'm going to be doing trip.where. This time what I care about is the start column rather than the duration column from the last question. And what do I want? I want all of them to start at SF Caltrain station. So if I just say SF Caltrain station, remember that the default thing for the where method is just to pick all of the, if I don't say r.anything, and if I don't say r.anything, then it just gets me every row that has this that has this value in the column that I'm looking at, right? So trip.where of start and SF Caltrain gets me every single row that started at SF Caltrain, right? Then what do I want? Well, I want the number of rentals that started here, okay? Which basically means that I just want the number of rows in this new table that I have where everything started at SF Caltrain. So once again, I'm just going to grab the number of rows of this new table, and that's the final answer. Next is the name of the station where the most rentals ended, and I am assuming no ties. So what I want is I want to find a new table that has a name of a station. So in the end column, I want the name of the station, and I want how many rentals ended there, right? So I have a whole bunch of different entries in this end column, right? And a lot of these entries are going to be repeated. So what I want to do is I want to group all of the unique entries in the end column together, and I want to count how many rows had that entry, right? So what I just said sort of hints the method that you want to use. So it's trip.group, right? We want to group by the end station. And what we want to do is we want to count how many rows ended at that station. So if I just say trip.group of end, that actually does that for me. What I'm going to end up with is I end up with a 2-column table that has end as one column, and it has count as my second column, right? So this table right here has all of my end stations, 1 row for each unique end station, and it has the count, which is the number of times that it showed up in the original table. Then what I want to do is I want to say, okay, since I care about the station where the most rentals ended, I'm going to sort by the count, okay? So dot sort of count. And if I say descending equals true, then the very first row is going to be the station with the highest count, which is the one that we want. So once we sort by count and descending equals true, then we just want to grab the very first entry in this end column. So dot column of 0, and then dot item 0, right? And so that's the name of the station where the most rentals ended. So now in this last bullet, we want the number of stations for which the average duration ending at that station was at least 300 seconds, right? So similar to the last one, now we want to somehow create a new table where each row has a unique station. And we also want to calculate like the average duration for every trip that ended at that station, right? So once again, we can use the group method to accomplish this. Once again, we want to group on end stations. And what we want to do is we want to take the average of all of the durations, right? So, you know, normally when we're doing group, a lot of times we've asked you min or max. But in this case, what we want to do is we want to take the average of every entry that corresponds to a particular end station. So to do that, we do np.mean. And actually, before we group, just to make our lives a little bit easier, we can select the 1th and the 2th column. So it selects the end column and the duration column, just so we don't have to worry about how np.mean treats this start column. You don't have to do this, but it'll just make your life a little bit easier, I think, just to select the 2 columns that you care about. Okay, so we've grouped on end stations, and we've taken the average of durations, right? So what our table kind of looks like now is we have a 2-column table of end, and we have the mean of duration, right? So now what we want to do is we want to find the number of stations for which the average duration ending at that station. So we're looking at these average durations, and we want this to be at least 300 seconds, okay? What we can do is we can grab the column with durations. So column 1, and we want to say, okay, is each of these elements at least 300 seconds? So greater than or equal to 300, right? This gives us, once again, an array of trues and falses. True if it's greater than or equal to 300, false otherwise, right? And so in order to count the number of stations for which it's true, we can say np.count non-zero of this whole thing, right? You could also use the where method. So what you would want to do is you want to say where elements in this column are greater than 300 and then count the number of rows. But this is a more efficient solution. All right, so this next question asks you to interpret a bunch of histograms. So we have these 2 histograms of bike trip durations. And we notice that in this first one, we have a bin width of 200 across the board, right? So 200, 400, 600, so on and so forth. But in this one, the divisions are between each of the lines, sort of. Well, it's between these lines, and it lies on 600, between 800 and 100. So this one has a bin width of 300 instead. All right. So between these two tables, which represent the exact same data, let's see if we can answer these questions that they have. So the first one asks us the proportion of trips that fall into the range between 200 inclusive and 400 exclusive, right? So, okay, it's a range of 200, which means, okay, I can look up at this one right here, 200 to 400, and we know that histograms include the left-hand side and exclude the right-hand side, which is exactly what we're looking for here. So, in order to get the proportion that's in this rectangle right here, remember that all we have to do is we have to multiply the x. So we say 200 multiplied by the y, so it looks like 0.15 here, okay? And this gives us the percentage of things that are inside this bin. So in order to get the proportion, I have to divide the percent by 100, and that's that. Next one is between 300 inclusive and 900 exclusive, okay? So this one starts at 300, which means, okay, maybe I'll start on this one. 300 to 900, well, I have 300 goes to 600, and 600 goes to 900. So, all I have to do to get 300 to 900 is just add up these two rectangles. So, I'll say I have a bin width of 300 for the first bin, and that first bin goes up 0.14 or so. And then I'll add the area of the next bin, which is 300 again, and I will multiply that one by its height, which looks like about 0.8 or so, or 0.08. And so this is the sum of these two bins that I'm interested in, and then to get proportion, once again, I need to divide the whole thing by 100. Next question I'm interested in is between 400 inclusive and 900 exclusive. Okay. Well, with 400, I can start on this left one, right? So I go 400 to 600, but then if I go 600 to 800, then I'm kind of stuck here, because 800 to 100 doesn't tell me anything about what goes to 900, right? Because my bin goes from 800 to 1000, and it says like 0.04% per unit there. You know, all of the mass could be shifted between 900 to 1000, or all of it could be 800 to 900. This bar doesn't tell me, right? So 400 to 600 is something I do know. Well, I can come over to this one, and this one goes from 600 to 900. So this one does tell me about 600 to 900. So by adding the proportion that are in 400 to 600 in this histogram, and the proportion that are from 600 to 900 in this histogram, because I know that the two represent the exact same data, I know that this is a valid way to calculate everything that's between 400 and 900. So I will say the bin width of the first, so that's 200 times the height of the first, so that's about 0.14 again, added to the area of the second bar, which is its width, 300, times its height, 0.08. And then I divide by 100. And that is the final answer for that one. Now we go from 200 to 300, right? Okay. So between 200 and 300, that means that I'm interested in this little sliver right here between the 200 line and 300 line. And how can I get that? Well, I can't do it directly by adding like I did in this one, because I have this first bar, I have this other bar, and you know, if I add the two, that doesn't really tell me much. But what I do know is that, okay, this is my 0 to 300 range, this is my 0 to 200 range. If I subtract everything that's in my 0 to 200 range, that only leaves me with things that are in my 200 to 300 range, right? Which means that if I take the bigger bin, 300 times 0.07 or so, and I subtract everything that's in the 0 to 200 bin, which is about 200 times 0.03, what I'm left with is just the things that are 200 to 300, right? Because, yeah, divide that by 100, and then I get my proportion. All right, so this next question is just a bunch of trues and falses about this particular study that's been done. So they followed 369 people with cardiovascular disease. They were randomly selected from hospital patients. And a year later, dog owners were 4 times more likely to be alive than non-dog owners. Okay, so true or false? This study is a randomized controlled experiment, and this is not true. This is false because the experimenters did not control who owned a dog, right? If it were a randomized controlled experiment, then they would have randomly assigned dogs to people or something, which is obviously not the case that happened here. Second one, this study shows that dog owners live longer than cat owners on average. This is definitely false because the statement that we are given tells us absolutely nothing about cat owners. So there's no way we can make any sort of assertion about the relationship between dog owners versus cat owners. The last one says that this study shows that for someone with cardiovascular disease, adopting a dog will probably cause them to live longer. This is also not true because this was not an experiment. This was an observational study. And because it was an experiment, we cannot say anything about causation. We can only draw correlative arguments. All right, so our last question is on sampling and hypothesis testing. Chancellor Dirks thinks that the choice of each customer is a random sample from a distribution over 5 outcomes. Fruit tea with probability 0.2, coffee with probability 0.15, milk tea with probability 0.2, classic tea with probability 0.4, and sparkling juice with probability 0.05. But Guy Fieri comes along and says that he doesn't think that customers choose classic tea with a 40% chance. He doesn't care about any of the other chances. He just thinks that classic tea isn't picked with 40% chance. So when he's investigating this issue, he's going to need a null and alternative hypothesis, and we have to figure out what those are. So the null hypothesis is just saying that, okay, over the course of my experiment, the data that I've collected only varies from what I would have expected from my initial assumptions due to random chance, right? So basically that's saying that our initial assumptions hold, right? So in this case, our null hypothesis is going to be saying that customers choose choose drinks from a distribution that gives classic tea a 40% chance of being picked, right? Because the data that he cares about is this classic tea with a 40% chance, and this is the overall distribution that was our initial assumption, right? And then the alternative hypothesis is just to say that something else is going on, right? So customers choose from a distribution, from a different distribution, right? So the alternative hypothesis basically just says that there's something else going on that's affecting the data that I've gotten. And so this would be a correct way of basically stating that in a succinct way. Customers are choosing from some different distribution. Okay. Now Guy needs a sample of customer choices. Each beverage cup contains a mark describing its original contents. And should he look in the garbage can outside of T1 at the end of the day and count the proportion of cups that contained classic tea, why or not? Okay. And so remember that when we're sampling, we want random samples, right? In this case, looking inside the garbage can outside of T1 at the end of the day is not a random sample. So no, this is not a good sampling scheme. Because this is what we call a convenience sample. So a convenience sample. Okay, what a convenience sample means is basically when he's looking inside the garbage can, there's nothing that specifically states that everything that was purchased that day goes into that one garbage can, and we don't exactly actually know how things end up in that garbage can, right? So because of the fact that it's a convenience sample, and we don't really know how the cups that end up in the garbage can are selected for that garbage can, this isn't a good sample for determining the purchasing habits of customers over all purchases from T1. And in C, T1 offers to give Guy a uniform random sample of 10 orders from his database of all past orders, and he says that's not enough, he needs a large random sample. And why does he need a large random sample? Well, the reason he needs a large random sample is, remember, we want to collect data that's representative of the overall population that we're interested in. And the overall population that we're interested in is just all purchases from T1, right? And in order to collect a sample that's representative of that, it needs to be a large random sample, right? Small random samples can have variations that throw off our data by a lot, but once it becomes a large random sample, then it becomes, it more closely resembles the overall population's distribution. So to justify that, we would want to say only for a large random sample will the proportions of different choices be similar to the population's distribution, right? So using a small sample, it's just much harder to say that the data that you've collected is actually representative of the overall population. So now the question is, should Guy use the total variation distance between Dirks' claimed distribution and the observed distribution as a test statistic? If not, why not? So first of all, we got to remember what total variation distance measures, and recall that the total variation distance came up in the jury selection problem that we had in the textbook and in lecture, I think. Basically, it's measuring the difference between two distributions, right? So it was like, how many members of my jury are African American versus how many eligible jury members were African American versus, and then, we also wanted to take into account how many eligible jury members were Asian versus how many Asians were actually on the jury panel, and so on and so forth. So what total variation distance actually measures is it measures the difference in distributions that arise between your null hypothesis and your actual sample. But in this case, we don't actually care about the overall distribution. We only care about the proportion of classic T that was chosen, right? So because we only care about the difference in classic T, we should choose something that's more focused on the difference between the classic T proportion versus the classic T proportion in the null hypothesis. So no, TVD would not be a good choice because it because it cares about the whole distribution rather than just one particular category. So a better choice would be to say, what's the absolute difference between the proportion of classic T in my sample versus the proportion of classic T in the hypothetical distribution, right? Which is distribution, right? Which is 40%. Right? All right, so now we've just got the last question in the practice midterm. And this is one that's asking us about calculation of p-values. So let's just remind ourselves of how we calculate p-values. Remember that what we do is we generate an empirical histogram of some values, and then we want to take a look at what test statistic our sample produced. So let's say the test statistic that my sample produces is somewhere around here. Then the p-value is just the proportion of things that are more extreme, so further to the right of this line right here from my overall histogram, right? So that's how we calculate a p-value. And so we see he's going through this process right here. He simulates the test statistic 100,000 times. So he's generating some histogram like this, where we have our test statistic as the x-axis, and then of course on the histogram the y-axis is the proportion. And then he wants to calculate the test statistic for his actual sample. T1 gave Guy a random sample of 100 orders, so it's a large enough sample that we can, draw some conclusions from it. And what's this test statistic? Well, the test statistic is the absolute difference between 40% and the observed proportion of classic T orders. In the sample that he got, 40 of the orders were classic T. So what's the proportion of classic T out of his sample? Well, it's 40 over 100, which is 0.4, right? So 0.4, And then the absolute difference between this number, 0.4, and 40%, well, if I convert this proportion to a percentage, then it's also 40%, and so the difference is 0, right? Which means that my test statistic from my sample actually lies right here, right on the origin. And so in order to calculate the p-value, we have to ask, okay, what proportion of elements in my empirical histogram are more extreme than this value right here? And the answer to that, as you can see from the graph, is going to just be 100%, right? Everything is as extreme or more extreme than the test statistic that I generated from my sample. So based on that, my p-value is actually 1, right? So p-value is 1. If my p-value is 1, then I cannot reject my null hypothesis using this 5% p-value threshold, right? So the choice here is B. And the reason I can't reject my null hypothesis is that since my p-value is greater than 0.05, the null hypothesis can't be rejected. I would reject it if the p-value was less than 0.05, right? Because that means the test statistic would have been all the way out here, somewhere out here, and that would mean that it's a very extreme value. But that's obviously not what we got. We got one that's way down here at 0, and so we can't reject the null hypothesis. All right. Hopefully this helped, and good luck on the midterm.